All right, so our first goal is to make this car jump off this ramp into that basket using physics. So to start, we have set the basket and the ramp 25 feet apart, and we're going to see how fast the car is moving at max speed. Okay, so now that we have our video, our slow motion video, we can put it into Logger Pro and plot as the car moves along all the positions that it's at right there. And go along with the video, click on the points and just advance a couple frames and plot a dot. And then we get a nice graph here. So you can see our Y isn't too important, it's just going to be the same because the car is on the ground. But X is increasing at a constant rate because the car is not changing speed. It's already at a constant velocity. So in that case, we'll just use an equation with x to the power of 1, which is y, or in this case, the name is x, but like the form of the equation would be y equals mx plus b. So we have x position and time here. So x position is the slope of the line, or the speed of the car, times time, plus, where it initially started. So if we calculate the slope of this line, we can get the speed at which the car is going forward. And we get it's about 44.48 feet per second. Calculate 10 meters, it's about 13.5 meters per second. So I can put that into my spreadsheet that I have from our projectile motion lab. And I can use the same thing, because this is just a projectile in motion too, propelled by a different source, but still. So I put it in here. I got values that were not exactly what I was looking for. They were a little too big. So I thought that I might have needed to change the frame rate of the video. So I divided it by 2. So that wasn't correct, but that's what I did at this point. But now we can get distance traveled based on every angle. To quick go through that, a little bit how that works. The equation that we'll be using for this is y, position y, equals initial position plus initial velocity times time minus 1/2 gravity times time squared. So the reason we're using this is because this is a particle or a projectile under constant acceleration. So we need to factor in acceleration due to gravity, which is right in this part here. But if we know that acceleration due to gravity, we can, and we know our initial velocity based on this calculation that we just did, we can calculate how long it will take in time to reach a certain y position. So if you imagine that when we're going to jump, the car is going to go forward, jump off the ramp, and then go down again. So we'll say that the time is 0 when it first hits the ramp. Now it's going forward. And we want to find how long it takes from when it first hits the ramp for it to get back to that same height, which means it's back on the ground. So if we just say y equals 0, then we'll get, then we can use this equation to find how long it'll take for the car to basically complete its entire jump and fall back down. And then if we add an offset to it, like make the initial height below, like however far below the target we want it to hit on the target. Like if the target's 3 feet tall, we'll just put it as -3. Then we can find how long it'll take to hit the target. So back in our spreadsheet here, we've done this using kind of a complicated looking Google Sheets thing, but it's basically just the quadratic formula that I showed you earlier, but kind of converting some things around. But now for every degree measurement, what we do is we can calculate how much of that velocity is going to be translated to vertical velocity. Because remember, it's going to be launched at an angle up this ramp here. So some of that speed that it's going forward will get going to up, and some of it will stay going forward. So it turns out if we take the sine of this angle, we can find out how much is going to go towards moving upwards, and then we know everything that we need to know for how long it's going to stay in the air. So that's what I calculated first, is just time in seconds that it's going to stay in the air. And then based on that, we can also find our x velocity, right? So some of this will get converted to up, some will get converted to sideways. The stuff that's converted to sideways is it's not going to be changing speed, right? Because there's nothing changing its speed. It's going at a constant velocity for a certain amount of time. So then all we have to do is multiply those two together to figure out the total distance that it's going to cover. And I got that in this column here. If I convert that to feet, we have that right there. And then so I could say like at 30 degrees, we think it's going to travel 15 feet just based on that velocity. So now we use those calculations, even if they were incorrect, to go about our next step. And this is the same table that we'll be using for all of our calculations going forward. Okay, so as you can see, most of those jump attempts were a little bit too far. And I really wasn't sure why initially, and I was feeling a little confused, but you saw that most of those attempts were off, but I did get one where I was able to hit the target pretty much just by chance. But I took that video and I plotted the positions of it in Logger Pro. So first I'll play the video. I'm going to take attempts at it until I get it. That was the worst possible playback of a video. But it hit the target, it took this path, and I ended up calculating a curve for the y and the x, and you can see it pretty much was going 27 feet per second, which is about half of what I kind of expected it to be going. I'm going to go into our calculator here. It's only 8.2 meters. I could actually also calculate, see how close it got to gravity. It's got 14.7 in there. This should be 4.9, but 4.4 is pretty darn close because I'm 1/2 gravity, 1/2 9.8 is around 4.9. So you can see that this curve actually is representing, or you're taking based on real world measurements, finding what gravity is, which that's pretty cool. But either way, we found that our speed was a lot less than I was expecting it to be. And so I was like, yeah, that's a little confusing, but I'd like to try it again and figure it out. But I don't know if you saw earlier, we did break a couple of different parts on the vehicle, and I bought some upgrades, and that ended up taking quite a while to fix. And also, the days just get shorter. Got activities after school, and I wasn't able to get around to doing this again for a little while. But that's about the update for this. So now we're back in Logger Pro, and this time, third try, I've been getting a little fed up with this. I gotta finish this up, and I decided to be extra diligent about it. So I started by just taking some straight passes to kind of see what our velocity was here. And as it turns out, still close to that 14.7 meters per second that we kind of calculated before. But I was just like, I know these discrepancies are just because it's losing speed on the ramp, so I decided to just calculate some trajectories based on jumps. I have two of them here. And based on those, I'm getting that our x velocity is going down to around 5.7, we can say, meters per second after hitting. So I'm basically just like, we're losing a certain amount of speed here. I decided to take 5.8 and divide it by cosine of 45 degrees, which is the angle there, to get 8.2 meters, and ignore that conversion down there. Sorry. To get 8.2 meters per second would be like our speed after hitting the ramp, but before, changing and splitting into x and y. And then I basically just decided, like, instead of hard putting that in there, I decided to just say it's around 4/7 of the total speed is what we're losing on the ramp. And I figured that would also kind of account for like losing slightly less speed with the ramp at lower angles. And at this point, I'm basically like, it's more of an approximations game than it is an exact science. And I just didn't really understand exactly how I would factor in like steeper angles, slowing it down more in like a useful way. So I decided to just stick with these approximations and then go on to do some testing because I know that this is getting me decently close. These two curves were based on that estimate as well, or I did some jumps that were based on that, and I was getting pretty close to landing these around like it was 20 feet between the wheelbarrow and the yellow thing, so it was like 27, 28 feet at like a 45-degree angle, and that was working pretty well. These are pretty satisfying jumps too. The car's got new parts in it, so I'm just like, time to finish this up. 25 degrees, 18 feet. $45 degrees and 25 feet. Okay, now we are doing 50 degrees, like 23 feet. Down at 20 degrees, we're only getting like 10 feet. Alright, so now we got 22 degrees and around 15 feet. Alright, this will hopefully be our last test. 28 degrees and 19 feet. Alright, so I'm back. I don't know if there's a ton else to show, just back in our graph. But as you can see, pretty much all our estimates were close-ish or accurate enough to get to get an accurate launch and a catch in the disc golf net. We didn't end up catching it. We always end up knocking over it, but that's all right. Can't get everything you wish for. So yeah, generally just kind of like to conclude, we were able to use projectile motion equations like these ones to calculate the distance necessary using a spreadsheet for a car or the angle necessary for a car to jump at any given distance. Okay, I have one more thing to admit. These videos were not recorded in one take, in case you were wondering. So to finish out, I think I'll play a little highlight reel of all the missed jumps before we ended up getting some hits.